We've been asked to determine if the given sequence of intervals is a nested sequence of closed intervals. So to check that they're closed intervals, we really just have to look at the end brackets. So we see that these end brackets are both square brackets, and so that automatically, by definition, tells us that these are closed intervals. So the more interesting part that we need to check is that they are nested, meaning that for all k that are natural numbers, we have I sub k contains the interval I sub k plus 1. So there's a couple of different approaches that we can take. We can algebraically reason with inequalities, or we can develop some intuition from the geometric picture. And so let's start with intuition. Let's think back to what we know about the graphs of the functions for these endpoints. So we want to graph the equations y equals 1 minus 1 over x and y equals 1 plus 1 over x. So a good place to start is this function y equals 1 over x. So this is a function that we should be able to stare at and know that it looks something like this. And then if we wanted to get the graph for minus 1 over x, we just take this first thing and we flip it over the x-axis, like so. But these weren't the graphs that we wanted. Ultimately, we wanted to add 1, and what that's going to do to the picture is just shift everything up by 1 unit. So both graphs will have these horizontal asymptotes. These y equals 1 lines, and then they'll just be shifted up, like so. Now, ultimately, we don't care about these inputs for the negative values. We're more interested in what these graphs are doing when x is a natural number. And so we can see here that the graph for y equals 1 plus, y equals 1 minus 1 over x, and the graph for y equals 1 plus 1 over x. Over here, these left endpoints are increasing as we go this way. And over here, the left endpoints are decreasing. And so this tells us that we can see that the left endpoints are decreasing and the right endpoints are increasing, which is telling us that as k gets bigger, the size of these intervals gets smaller and smaller. They're shrinking. And so this leads us to believe that indeed they are nested. As for if they're non-empty, we can also see from this picture that we're expecting this one is approaching 1 from above, and this one is approaching 1 from below. And so this is going to tell us that these are non-empty, and it leads us to believe that 1 is contained in all of these intervals. So now we've used the graphs of the functions for the endpoints to justify our intuition, but that in itself was not a proof. What we're going to do now is use some manipulations of inequalities to actually prove the things that we believe. So the first thing to check is that 1 is in I sub k for all natural numbers k. Okay, so we need to check that 1 is in all of these intervals, and so let's start from some inequalities that we know. We know since k is a natural number that 0 is less than k, and that tells us that 0 is less than 1 over k. And from this, we see that negative 1 over k is less than 0, is less than 1 over k, and we can just add 1 everywhere in these inequalities. And then we have the freedom to change these strict inequalities to weak inequalities. So change all of the less than signs to less than or equal to. This is a more lenient condition. So then by definition, 1 is in I sub k. And then we also want to check that I sub k contains I sub k plus 1 for all k in the set of natural numbers. And so we can again start from an inequality we know, like k is less than k plus 1. And this tells us, by dividing both sides by k and k plus 1, that 1 over k plus 1 is less than 1 over k. And then we see that this tells us that 1 plus 1 over k plus 1 is less than 1 plus 1 over k. Similarly, by starting from this inequality, multiplying both sides by negative 1, we're going to get that negative 1 over k plus 1 is greater than negative 1 over k. And then we can add 1 to both sides. So this tells us that 1 minus 1 over k plus 1 is greater than 1 minus 1 over k. And we can put all this information together. So we see that if we have 1 here, we know that 1 plus 1 over k plus 1 is bigger. And then comes 1 plus 1 over k. And then on the other side, we have this 1 minus 1 over k plus 1. And we have our 1 minus 1 over k. And so graphically, it helps us see that we have this interval here, I sub k, and we have this smaller interval here nested inside, I sub k plus 1. And then in both of them is 1. And so this works for any natural number k. And so we've really shown, yes, this is a nested sequence of closed intervals. It's non-empty for all k and n. In particular, it contains the number 1. And then that answers that last part.